speaker for today's Matrix Symposium seminar series. Namkoong, or Hong, is an assistant professor in Decision, Risk, and Operations Division at Columbia Business School, and he's a member of the Columbia Data Science Institute. His research interests and expertise lie at the interface of machine learning, operations research, and causal inference, and his emphasis is on developing reliable learning methods for decision-making problems and solving decision-making. His research has been recognized by many different conferences and awards, including Neural Information Processing Systems, International Conference on Machine Learning, Informs Applied Probability Society, and Conference on Computer Vision and Pattern Recognition. He also has the Amazon Research Award. He received his PhD from Stanford University and before joining Columbia, worked as a research scientist at Facebook Core Data Science. Outside of academia, he also is a LinkedIn scholar in LinkedIn's Trust and Responsible AI team. It's a great pleasure to have you here with us, Hong, today, and we look forward to hearing your talk on adaptive experimentation at scale.
Thanks, Mina, for the kind introduction, and thanks for the invitation to speak here. So I'm going to talk about a research direction that I'm actually quite excited about. This is actually the very first time I'm giving a talk on this direction, so I'm all ears if you have any feedback. And the reason I'm excited about this direction is really because it poses a new way of thinking about a rather classical problem. And it feels like the beginning of a story rather than the end. So the work I'm going to talk about was led by my student Ethan Che. He's been fabulous during the project, and I hope I can do his work justice. I'm going to talk about a lot of different empirical demonstrations throughout the talk. And if you want a nice summary of, Ethan made this interactive plot where you can look at all the figures in one go. So it's on my webpage, and it's also in the paper if you want to take a look. Okay, so diving right in, let me perhaps open with a pretty concrete example. So imagine you're a machine learning engineer, right, on a social network, one of these online platforms, right? Now, if you're an ML engineer, right, you often train a prediction model to predict short-term outcomes that are rather frivolous but abundant. So for example, in this context, right, let's say that on Facebook you have, say, friends you may know type of a recommendation system. Then what are you trying to predict? Well, you're trying to predict whether people are going to click on these types of recommendations. And if I click on the recommendation, are people going to accept my invitation to be a friend, right? And once you become friends, are you going to start talking to each other and engage in meaningful social interactions? Now, while these machine learning systems are actually trained to predict these short-term outcomes, you don't actually really care that much about predicting clicks. Okay. So if you're the ML engineer in this scenario, there's a bunch of these outcomes you can potentially try to predict. And of course, there's about 1,000 different approaches for approaching this prediction task. And in the end, you have a bunch of different configurations of the recommendation system that you can potentially deploy. Now, how do I actually link all of these different configurations to long-term metrics that you actually care about? Because again, you ultimately don't really care that much about predicting clicks, but you do care about whether this recommendation system is actually having a meaningful impact on users' experience on the platform, right? So this could be onboarding new users and letting them grow their networks on the platform. It could also be increases in the amount of meaningful interactions they have on the platform, and so on and so forth. And the reason this is a rather complex problem is that if you really think about it, no matter how good a machine learning engineer you are, right, the biggest impact you're going to have on people's experience on the platform is rather small, right? You're going to improve these long-term metrics by something like 2%. That's not, that's not a very large effect. And what that means is that you're almost always in an underpowered statistical scenario, right? Samples are quite rare. Statistical power is a concern. Okay. So again, the main takeaway here is that these ML systems, they're trained to predict these short-term outcomes that are abundant yet frivolous, and to connect these to actual decision-making, stuff that actually matters, that you care about. People use experimentation, A/B testing. So it's the de facto standard interface between machine learning and decision-making right now. And of course, moving beyond the world of online platforms, right? Experimentation is the foundation of all scientific decision-making, right? So experimentation is used to evaluate medical treatments, economic policies, product and engineering innovations alike. Right? And if you think about, say, clinical trials, of course, experimentation is expensive or risky. But even in these online platform examples, right, in the process of experimentation, in the process of the A/B test, you really don't want to hurt users' experience. So these actually pose a rather stringent operational constraint, okay, on the sample size. So when these treatment effects are rather small, right, statistical power is of fundamental concern, and the sample size is actually a first-order problem. And to deal with this issue, there's actually been thousands of different papers on the topic. So the main idea of this entire literature on adaptivity is to observe a set of outcomes for these users, and then use this information in an adaptive manner so that I can rule out the most horrible looking treatment arms, and then really focus measurement effort, right, on the most promising arms, the exploration-exploitation trade-off. So, of course, I'm sure a lot of you have heard of the term multi-arm bandits, right? So that's a huge literature. It's essentially a field by now. And the de facto standard there is to assume continual reallocation at the unit level. So what I mean by this is that every time I see a user, I'm going to see the reward that I get corresponding to the treatment arm I assign to this person. And then I'm going to use this reward to update what I'm going to do to the next person. This is the idea of adaptivity, right? And these types of algorithms are largely guided by theory, because if you think about this problem, right, if you have, say, 500 different people in your clinical trial, it's a 500 horizon dynamic program. That's super hard to solve. So a lot of smart people have designed lots of different approximation guarantees that essentially say that as the number of reallocation opportunities grow to infinity, you get some good performance guarantee. So it's a big O type of guarantee. Okay. But the problem with these types of algorithmic design paradigms guided by theory is that in practice, you often care about a lot of different objectives. For example, you might, in any experiment, the goal is to pick the right treatment arm at the end of the day, right? That's the whole point of you running an experiment. But at the same time, you might also care about not introducing too many negative experiences for the trial participants in the meantime, right? So there's a tension between these two, because in order to actually explore and learn which treatment options are good, you fundamentally have to make mistakes, right? And how do you balance them? Each person is going to have their own preferences. And for each preference, you're going to have to design your own algorithm. And then there's certainly a lot of different papers in this literature. Okay, so this is sort of the status quo. By the way, for those of you who just joined the room, please feel free to stop me and ask questions. It's my understanding that this is an exceptionally broad audience. So please stop me if you have any clarification questions, or if you want me to go over anything in more detail. Okay. So now let me talk a little bit about what actually happens in practice. Okay. So in reality, in these application scenarios, reallocating measurement effort is actually quite costly. So if you imagine, say, economists or statisticians working on real RCTs, randomized control trials, right? These economists, for example, go to individual villages in Indonesia, right? And you have to somehow look at the previous measurements to update your policy, how you're going to assign the treatment arms right now. So naturally, that's a very labor-intensive process, and you can easily imagine biostatisticians working with clinical trials, that can also be a fairly costly thing too. And even in these online platform examples, right, in tech, where everything is supposed to be automated, this is actually quite difficult, reallocating measurement effort. So it's often the case that the experimentation infrastructure at these companies, even the larger companies, right, it's actually quite cumbersome. So deploying a single feature, right, and making sure that this gets deployed to the app in an efficient way, these are fairly well-established pipelines, but actually running an experiment and then updating your measurement policy and so on, it doesn't really play nice with the current tech stack that these companies have. So there's significant engineering difficulties to reallocating measurement effort. So forget about doing this, right, for every single user on Facebook. That's just going to be really hard. And of course, a lot of these engineers that be working at these organizations, they work in 6-month cycles, right? So you come up with some feature, you run an A/B test, check whether it's actually effective, right? And if your ML-based recommendation system is actually giving benefits to people, then you deploy it, you get some performance rating, get a bonus, and move on. Is sort of what happens at these companies. So people don't really have a major incentive to continue exploring, continue experimenting, right? So T, the capital T, is not going to grow to infinity. Okay. And there's also a lot of delayed feedback in the outcomes that you're interested in the sense that the outcomes you're interested in are things like how many times did the user use this product in the last 2 weeks, right? So it by definition requires 2 weeks to measure. So for each user, you're not going to wait 2 weeks to see what happens to them and then update your policy based on it and keep on doing this. So all of this is to say that the number of reallocation epochs in practice, it's extremely small. It's something like 3 or 4. And in each epoch, right, a lot of these outcomes are measured in very large batches. And the conventional wisdom in the literature is that these types of batching, right, it complicates algorithmic design. And there's definitely a lot of works on this topic of batching as well, right? But because things are just complicated in general, this notion of adaptivity, it's rarely used even on these online platforms. So in my experience, 99% of all experiments are just simple static A/B tests, simple RCTs. Okay. So today I'm going to talk about how we can formulate this problem of adaptive experimentation into a format where we can actually optimize the so-called constants, right? So before, the number of reallocation epochs were growing to infinity, and people wrote down these big O notation to show fancy theory. Now, I'm claiming that all you care about is constants in practice, right? So we want to build algorithms that are tailored to the small number of reallocation epochs, say something like 3, and you really want to tailor to the specific, instance-specific signal to noise ratio of your problem. Okay. And the reason I really want to write down a clean formulation, clean optimization problem for adaptive experimentation is because I don't think algorithms should be designed by theoreticians like myself. Okay. I think algorithms should be designed by computational tools. And by now, right, we certainly have really good tools in machine learning and optimization. Right? If I can get the experimenter to write down what their objectives are and what the constraints are. For example, is this new product draining the app's battery a lot, or is it introducing latency? Right? So there could be a lot of these types of side effects, even in an online platform, for example. So you might care about the safety during the experiment. So you want to encode these objectives and constraints in a flexible way, right? Pose this as a single optimization problem, then put on your ML hat, and then go, okay, how do I come up with the best experimentation strategy there? That's what I want to do. And any algorithm that we derive at the end of the day, it must be able to handle any batch size in a flexible way. Because if you imagine working at these types of online platforms, right, you're simply not going to be able to control how many people use your product on any given day. Okay. It ranges from anywhere from 1 million to 150 million. So this is sort of the goal of the talk. And the main idea of this paper is actually very simple. So let's say that we have 3 batches. Okay. 3 opportunities to adjust your experimental design. Now, here I have the blue arm and the pink arm. So these are different configurations of the recommendation system in the example I gave at the beginning of the talk. Right? And in each batch, what I'm going to do is I'm going to aggregate the rewards that I saw in the entire batch. Now, using the central limit theorem, any sample mean, any aggregate, right, I can approximate using a normal distribution. That's what the CLT tells you. So in a picture, right, what I'm showing here is that for the blue arm, I have this bell curve describing the distribution of the aggregate rewards that I see in the first batch. And I have a corresponding bell curve for the pink arm as well, right, in batch 1. And as you can see, the fatness of this bell curve is it's modulated by the proportion of times you pull each treatment arm, the proportion of times you assign each treatment arm. So in the first batch, I happen to assign the blue arm a lot. That's why you see the skinny bell curve, right? There isn't much noise. But the pink arm, you didn't get to observe that much. That's why the bell curve is rather wide. Okay. So now what I've done is I've reduced the problem. That's a very complicated dynamic program, something that's somewhat mind-boggling to even think about, into this 3-stage sequential problem, where at each stage, I just see a Gaussian observation. Okay. So it significantly simplifies how you can look at things. So in that sentence, right, as I've written down here, the idea here is that normal approximations, right, that's universal in statistical inference. Of course, this is how we calculate p-values and test hypotheses. The main idea of this paper is that it's actually also useful for designing adaptive experimentation algorithms. Okay. So let me actually pause here in case there's any questions. If anyone wants me to repeat the main idea of this paper, I'm happy to do that too.
A quick question, Hong. For the Gaussian sequential experiments, are you limited for the types of data sets you can apply this for the A/B testing as an example?
Good. Effectively, no. So anything you're going to use normal approximation to do statistical inference for, meaning anything you're comfortable with applying regular p-values for, you'd also be comfortable applying these types of bell curve approximations. Thanks, that's a good question. So one notable exception is that if your outcomes are super heavy-tailed, for example, on these online platforms, usually it's the number of friends that's super heavy-tailed, right? In those types of instances, these types of approximations are usually not appropriate. Okay. Good. So let me now try to formalize things a little bit. Okay. This is actually a very careful formalization. And the main conceptual difficulty here is that these normal approximations, they hold, right, when you have large batch sizes, when the batch size is large. And this is fairly natural, right, especially in an online platform example, because you have a lot of users. But then, if you think about it, right, if the batch size scales to infinity, then you're done, right? There's no adaptive experimentation to talk about. You already have a lot of samples. So in some sense, to come up with a non-degenerate problem, right, to come up with a meaningful formulation, you need to look at correspondingly difficult examples. And this is actually a very, very classical idea. This is the way that statisticians formalize the notion of power tied to error. Okay. And the main idea here is that we're going to model underpowered experiments that naturally arise in practice. And again, these happen even when you have a very large batch size. And the way we're going to model this is by scaling the average rewards to go down as you get larger batches. Okay. This is just a theoretical way of thinking about things, right? A particular scaling. And the idea here is that if the gaps in the average rewards, right, if the treatment effects are smaller than 1 over square root of n, then you're dead. No amount of experimentation is going to help you, right? You can't tell these gaps apart. On the other hand, if the treatment effect is a lot larger than 1 over square root of n, then the problem is trivial, right? You don't need any adaptivity. So in some sense, the interesting regime is when the average rewards scale like 1 over square root of n. Okay. So the model that we're going to posit is that the rewards that you see for the treatment option A, small A for arm or action, right? It has mean h over square root of n, okay? So I'm just scaling the mean as 1 over square root of n, okay? And some idiosyncratic noise. So this is the reward model. And for simplicity, I'm going to assume that the measurement noise is known here, that the variance of these noises are known. And of course, this is never known in practice, but this is something you can actually efficiently estimate in practice. And I'm happy to talk about this in detail offline if any of you are interested. Okay. So this is the reward model. I'm going to assume that the average rewards, right, they go down as your batch size grows. And of course, in any practical problem instance, n is finite. But this is just a particular abstraction. So then, if you imagine the first batch, right, I observe a whole bunch of rewards for the blue arm, the pink arm, and so on and so forth, right? And for each of these arms, I can aggregate all the rewards that I saw as a sample mean, okay? I'm going to call the sample mean R bar, okay? And by the CLT, I can approximate it using some normal distribution. The details of this doesn't matter too much. What does matter is that you understand where the CLT comes from, right? The CLT comes because n, the batch size, is growing. Okay. So now what's beautiful about this is that instead of having a problem defined over these n people, now I have a problem defined at each batch, right, over these Gaussian draws. I just see, if I have the blue arm and the pink arm, I just see two normal draws, and this is my observation. And the proportion of times I told arm A, that's pi t in my notation here, this is what controls the effective sample size, right? The fatness of this bell curve. If it's very flat, it means that I didn't get to pull this arm too much in this batch, right? So probably in the next batch, I should try a bit harder. Okay. And the main idea here is that by looking at this as sequential Gaussian draws, right, I'm going to try to glean some information off of the mean of this Gaussian draw, right, which involves h, the quantity of interest in this experimentation. Okay. Now here's the main theorem in this paper, which is a formalization of what we just talked about. Okay. So these individual aggregate batch rewards, right? I just told you that we can approximate it using a normal distribution. I'm going to call that normal distribution GT, okay, G for Gaussian. So let's say that at each time you observe these Gaussian draws, right, G0 to GT. Then what this theorem tells you is that these batch aggregate rewards, these sample means that you calculated over each batches, right, it converges to this sequence of Gaussians. In case we have statisticians in the room, this is essentially a generalization of the usual local asymptotic normality regime. So local asymptotic normality is the theoretical language that statisticians use to formalize these notions of statistical power. Right? If you're trying to tell apart two different hypotheses, right, the null versus the alternative, then if they're very far apart, you're done, right? The confidence intervals shrink at the 1 over square root of n rate by the CLT, right? So if they're very far apart, you're done. So in some sense, the only way you can quantify statistical power in this language of asymptotic statistics, right, is when as n grows, right, as your confidence intervals shrink, this alternative moves along at the same rate, right, toward the null. So it's a very classical topic that actually we teach to even first-year PhDs in statistics. And this is a adaptive experimentation version of it. Okay, it's a generalization of that framework. Any questions on this asymptotic result?
No, I don't think so. You've explained it very well. Thanks.
Thanks. Okay, so now given this Gaussian approximation, what we're going to imagine is a experimenter having a prior over the average rewards. So H, again, was my notation for the average rewards, right? The thing you're trying to do inference on. And if you think about these typical online platforms, they literally run thousands to hundreds of thousands of experiments each year. So it's plausible that any experimenter can formulate some notion of a prior over these average rewards, right? And of course, in scientific studies, this is even more plausible. Okay. So now, as my objective, as the objective of the experimenter, we're going to look at a particular objective for simplicity. And this objective looks at the arm that has the highest mean, right? This is the best treatment option that you could have chosen, the max over H's. And then it compares this to the thing you chose, which is A hat. Okay. So this is the optimality gap. And as a corollary of the theorem that I stated in the previous slide, right, what you can show is that in reality, right, if you have a policy that looks at the previous sample means to update what you're going to do right now, right, the performance of this policy can be approximated by that of the similar policy, right, that instead of using these sample means, it actually uses the Gaussian draws. Okay. Let me say it again. The performance under the policy using these batch aggregate rewards, right, it can be approximated by the performance of the policy that uses these Gaussian idealizations. And these batch aggregate rewards, of course, in practice, I don't really know what the distribution of that is, but what this corollary is saying is that Gaussians actually provide a very good approximation to this. So what this now means is that I can look at this approximation, the performance of the policy under the Gaussian idealization, and then try to optimize for the bestest policy. Okay, so this is the optimization problem I've written down on the top blue box, right? Pi is my sampling allocation. And again, the objective is this optimality gap. And here what we're saying is that each time we're going to observe a Gaussian observation. Okay. And then using these Gaussian observations, I can perform posterior updates on what I think the average rewards H looks like. And in particular, for those of you who've heard of multi-arm bandits, right? In that literature, the standard thing is to look at each individual person's reward instead of this average, right? And then to try to model each individual person's behavior. So naturally, this is fairly hard, right? And for these algorithms like Thompson sampling to work well, these classical algorithms, you fundamentally have to have a really good model of each person's behavior. Whereas in our framework, because we're just aggregating everyone in a single batch, right? I only need to have a belief over the average rewards. So this is a major practical advantage. And as you can see, right, the signal to noise ratio of the problem, right, and the small number of allocation opportunities, it's all embedded in the sequential Gaussian experiment G. And the part that I initially talked about, right, about how I want to use computational tools to derive good policies, it's already somewhat evident here, in that this is a complete minimization problem. I can now put on an ML hat and go, I want to find a good policy that solves this minimization problem. And there's a number of different ways of doing this, and that's what I'm going to talk about now. Okay. And the great thing about this formulation is that once you come up with a pi that you actually like, that kind of approximately solves this minimization problem, then this pi, given the history, is just a fixed probability. If you have 100 arms, 100 treatment options you're considering, it's just a probability over those 100 probabilities. So it's something that you can very, very easily deploy in these online platforms. Okay? If you update your policy, say 5 times, in these online platform examples, you're probably gonna say on a Thursday 3 a.m. when no one's using your platform, you're gonna look at the previous examples, use it to update your policy, and then you're gonna deploy that fixed sampling distribution and use it for the next week. Okay, and then you do this maybe 2 times or 3 times. So it aligns very well with the existing experimentation infra. Okay, that's the point of this this slide. Okay. Now we kept on using these asymptotic approximations, right, to derive this this minimization problem. So one concern here might be, okay, but in practice, right, your batch size might be pretty small. Imagine you're not in an online platform setting, but imagine you're a political scientist designing an adaptive experimentation, right? Then the batch size is pretty small. But surprisingly, what we see is that the performance, right, that's approximated under the Gaussian idealization, that's the blue, the green bar here. I'm plotting the histogram of the objective that we want to optimize, okay, over the prior. And here what we see, right, is that this is a problem where you have 100 different treatment options, right? So that's a lot of different arms. And if you look at the pink bar, I wrote down that the batch size is equal to 100, right? So uniform allocation only assigns one person to each arm. So that's a crazy small number of samples. But even in this very small sample regime, you can see that the Gaussian limit actually provides a fairly reasonable approximation. So this kind of confirms this folklore that statisticians have, that normal approximations, that the central limit theorem, actually is kind of reasonable, even for small batch sizes. So when I talk to my colleagues in statistics, they kind of tell me that, you know, CLT, it kind of kicks in when n is something like 30. It kind of depends on the distribution, but when you're at 70, it's almost always very closely approximated by a normal PDF. And we indeed see something like this happening here. Okay, so now given this this sequential minimization problem that I just wrote down, let me actually instantiate this so that we can put on an ML hat and try to derive concrete adaptive experimentation algorithms. Okay. So now I have a bunch of math, a bunch of equations on this slide, but the message is actually quite simple. Okay. So we're going to assume that the experimenter, you, have some prior on how good each arm is going to be. Okay. So I'm going to denote this probability, right, as a normal distribution with mean mu0 and variance sigma 0. Now, what we just saw from all of these normal approximations, right, was that G, this idealized Gaussian observation, right, given H follows a normal distribution. And if you remember, right, in the sample mean CLT slide, this normal distribution is exactly what I have, the second normal I have up on the slide. Okay. So then we have a prior and likelihood that are both Gaussian. And if you beckon back to the very first time you took statistics, I'm sorry to bring up these harrowing memories, there's these posterior updates for these Gaussian conjugate pairs that you can do. And it gives you this very, very neat formula where the posterior variances, right, in this Gaussian scenario, it's actually deterministic. And you can sort of see how they shrink over time, right? 1 over sigma squared is kind of going down over time. Oh, sorry, it's blowing up over time as you keep adding things. And the posterior mean, right, it also evolves based on GT, the observation that you saw, the Gaussian observation. So now the point here is that these are the states of the system. I have a 3-stage dynamic program where each step, right, the system can be perfectly characterized by the mean and the variance. That's the beauty of these Gaussian approximations. So here's the posterior states again, right? And GT, right, it's some Gaussian distribution. And I'm going to do a change of variable. So instead of a regular normal distribution, I'm going to use a standard normal distribution with mean 0 and variance equal to 1. I'm going to call that ZT. And if I do that change of variables, I get some weird looking formula. It doesn't really matter what that formula looks like, right? But the important thing here is that you can see that mu t evolves as a random walk, meaning that every time you see some ZT, right, this normal standard normal draw, that's what modulates the step size in this random walk. Okay. So now again, I have, say, a 3-stage or a 5-stage adaptive experimentation problem, and I can succinctly write this as a Markov decision process, as a very concrete decision-making problem. Okay. So this is sort of a standard formulation that you'd write down if you work in reinforcement learning. So the objective here is the best arm that you found at the end of the day, at the end of the experiment. That's what mu t is, right? Mu t is your current posterior belief on how good each of these arms are, right? And you're taking the maximum over all the arms you saw. So this is the reward you're going to get at the bottom of this slide, right? And I want to maximize the reward you get at the end of the experiment, right? By somehow coming up with good policies pi t, right? Good sampling allocations. These are just probabilities, right? Over the 100 arms you have. Okay, so this is a very concrete Markov decision process I've now written down. Okay. So here I'm saying the same thing. And for those of you who know what dynamic programs usually do, right, you often want to write down the value function. So the value function is simply the amount of expected reward you expect at the current state. So let's say that your current belief about the system, meaning how good each of these arms are, right, that can be summarized, as I just talked about, as your posterior belief mu and sigma. So this conditional expectation is your value function. And because of this recursive formula that I have in a pink box at the top of the slide, right, I can now expand this mu at capital T into this sum. Okay, it kind of looks pretty complicated, right? And indeed, optimizing this as is, that can be pretty hard. So somehow I need to come up with an approximation scheme in a computational way. So now I'm going to put on an engineering hat and then think about, instead of a statistician hat, right? So instead of doing theory, I'm now going to go, okay, how do I come up with a reasonable minimization scheme or a maximization scheme for this reward? Okay. Now, before I talk about specific algorithms, right, specific computational approaches, that's actually not the main point of the paper. The main point of the paper is that this is actually a pretty useful way of looking at adaptive experiments. So despite the conventional wisdom that batching is something that potentially introduces complexity, right? In our formulation, batching, it simplifies by a great margin the algorithmic design. Because now I just have Gaussian observations. So instead of assuming that the word is Gaussian, which is usually a common assumption in these theory papers, Gaussianity is a result of the central limit theorem, not an assumption, right? And our formulation, it allows you to incorporate prior knowledge on these average rewards that these experimenters are going to have, right? And if you look at this dynamic program that I just wrote down, this Markov decision process, it's fully differentiable, meaning you can use PyTorch to optimize this. And you can, again, bring to full power these modern machine learning and optimization tools. Okay. So I'm going to talk about a very particular algorithm today, but smarter people than I can come up with better algorithms, I think. And I think that's what's really exciting about this formulation. That now I can go to my engineering friends and go, can you find me a better policy in this regime? And here's a starting point. So what's our starting point? So solving a dynamic program in general, it's pretty hard when you have continuous states like in our case, right? So I'm going to consider what's known as a open loop policy. So I'm sure this is a standard thing for the EE folks in the room. But for the non-EE folks in the room, I'm not a EE person. An open loop policy is just a simple optimization scheme that considers what you're going to do in the future, right? And these future allocations, how you're going to sample these different arms, you're going to say they don't depend on the future information, right? The future you is only going to look at the information that you currently have. So this greatly simplifies the problem. So in this value function, right, I'm saying that these future allocations pi v doesn't depend on the future states at all. not a function, it's a constant. That's what I'm assuming in this optimization problem. So naturally, I'm not going to be able to plan in the most optimal way, right? This is a very crude approximation. Okay. So instead of pi v, which is a function, I'm going to replace it with a rho v, which is a number. Okay. Now I just have a number. Now, the sum of normal variable z is also a normal variable. So I can reformulate this problem in this very, very simple way. Okay, so this is the final maximization problem I gotta solve, where it says, right, that at the current state, mu and t, mu and sigma at the current time, small t, that's what's in the conditioning, right? I want to imagine what's going to happen to my posterior reliefs over the remaining horizon in the experiment. And you can see that this optimization problem really takes into account, right, the residual horizon that's left. T minus small t is the number of time steps you have left in this experiment, right? And you can see that this algorithm really tries to take this into account. If you don't have that many time steps left, then your best bet is to focus on maybe the top two arms and trying to figure out which one is better. But if you have a lot of time steps left, then maybe you should spread out your measurement efforts. This is what this algorithm tries to do. Okay, so this is a very particular stochastic optimization problem. You can I can essentially ask a master student to try to optimize this using standard PyTorch tools. Okay, so it's something that you can do as stochastic gradient descent on. It's something that's quite easy to optimize. And again, the idea here, the one-line summary here, is that this algorithm, it calibrates how much you want to explore all the treatment options, right? Depending on the residual horizon, the amount of sampling opportunities you have left. And the main advantage of this algorithm is it's actually very, very easy to implement and deploy in practice. So imagine that your current sampling allocation is this probability rho t, right? So it just means that you have a probability over these treatment arms, 100 treatment arms. So every person who comes in, you're going to draw an arm from this probability distribution and assign this person that particular treatment option. Now, on a Thursday, 3 a.m., what you're going to do is you're going to look at all the people you saw in the past week, aggregate their rewards into a single number, right? Take the sample mean, and then use this to update your posterior reliefs, right? So that's how you end up with these posterior reliefs. And then you're going to plug in these new posterior reliefs in the optimization problem that I had before, right? This guy. And you're going to run SGD, stochastic gradient descent, to solve for the right row. So that's the policy you're going to use the next time. And this part is something that's very easy to do, aligns very well with standard ML infra. It's something you can run at Thursday, 3 a.m. And then at 8 a.m., the engineer can come in, check whether the training run was actually good, and the engineer can deploy this on a Friday morning. Okay, so something, again, that plays very nicely with the current tech stack. Any questions about this this overall idea? Good. All right. So maybe skip this in the interest of time and show you one plot that allows us to build up intuition on what this algorithm tries to do. So I just told you that this algorithm, residual horizon optimization, right, it calibrates the amount of exploration you want to do to the amount of exploration opportunities that's left. Okay, so if you only have one time step left, right, if the experiment has to end in the next batch, that's what this scenario is on the left-hand side, then you can see that the probability that this algorithm assigns to these 5 arms, right, it's only positive in arm 2 and 3. Why? Because it believes that these are the arms that are the most promising, And it wants to, in the remaining batch, figure out which one is better. Okay. But then if you have a ton of exploration opportunities left, right? You have 10 steps left, then you can see that it really spreads out the exploration effort. So it really takes into account the amount of horizon that you have left. And this is actually not a behavior that you see when you look at classical algorithms that assume that your horizon is blowing up to infinity. Okay, so now let's take our algorithm and compare it to the algorithms that we have in the literature. So one thing to note again here is that these algorithms are actually quite difficult to implement in practice, and that's why a uniform allocation, a static A/B test, is the de facto standard. Okay. In addition to that uniform, we're going to look at a bunch of different benchmarks. The one benchmark policy that's actually quite popular in practice is an algorithm called successive elimination. So what this algorithm does is after each batch, it looks at the arms that are hopeless and it just eliminates them, right? So if you have arms whose upper confidence bound on the rewards, right, are lower than the lower confidence bound on the other arms, these arms can be safely ruled out. So that's the main idea about behind this algorithm. And then the bottom two policies are Bayesian policies that maintain a prior on the individual rewards. So it requires a very fine-grained assumption on how people behave, how individuals behave. Okay. And of course, you expect our approach to work really well, right, when you have a large batch. So here we have 100 arms, treatment options, and 10,000 batches, 10,000 batch size, okay, n is equal to 10,000. And on the y-axis, I'm plotting the percentage improvement, right, over the uniform A/B test, over what you're going to do in practice right now, right? And you can see that even compared to these oracle policies that assume perfect knowledge of the world, right, basically this green line is far, far below everyone else. And it's kind of what you expect because the batch size is really large here. But now let's imagine a scenario where the batch size is small. Okay. So we're going to drastically reduce the batch size in this example from 10,000 to 100. Remember that we have 100 arms here. So a uniform allocation is going to assign a single person to each arm, right? The effective sample size is 1 here. So it's not a large batch limit. It's a very, very, very small batch setting. And even in this extreme case, right, you can see that our algorithm performs very well. You sort of see that it's a very robust algorithm. Okay. This idea of planning in this iterative way, it seems to be quite powerful. Now, maybe before I end, let me show you one final thought, which is what happens as the system gets noisier. So if you have the signal to noise ratio in the system degrade, right? You can see that conventional algorithms sometimes work quite poorly, algorithms like successive elimination. But then our algorithm, right? You can see that in all of these settings, its performance degrades for sure when the variance increases, as you would expect. But, by the way, this is the percentage of the performance of uniform, and then here lower is better, right? So that's why the blue bar is staying the same, right? And lower is better. And you can see that our algorithm actually performs really well, right? Under all measurement noise settings. And although this is a relative comparison, if you look at the absolute error bars, you can also see that our algorithm really dominates when the measurement variance is high, when the signal to noise ratio is very low. Okay. So this idea seems to be a very robust one. So just quickly summarizing these empirical results, and again, we have a very nice interactive plot in our web page. The main takeaway here is that this notion of Gaussian approximations, this Gaussian sequential experiment, it actually provides a good framework for designing adaptive experimentation strategies. And what we just saw is that this Gaussian sequential experiment is actually surprisingly a good approximation, even when batch sizes are exceedingly small. Okay. So policies that are derived from our Markov decision process, this dynamic program, right? It tends to outperform algorithms that require even more stringent knowledge of the world. And among these policies, right, I gave you one particular policy that I actually happen to like, which is what we're calling RHO in this paper, right, Residual Horizon Optimization. And I just told you how it achieves pretty big performance gains over the status quo. Okay. Good. So just to wrap up, we talked about a formulation, right, where we can really design algorithms using modern computational tools, right, rather than through the use of theory. And there's certainly a ton of different algorithms in this literature that are optimal in theory, but no one would ever, including the authors, would ever think about implementing these algorithms in practice. On the other hand, right, in our case, the algorithms that we developed, there aren't theoretical guarantees on these algorithms, right? However, I derived them using these machine learning and optimization tools, right? Basically PyTorch. And I can show empirically, as I just showed you, that it reliably works. I can spur empirical progress by benchmarking, which I think is the key formula to having a practical impact these days. Okay. And again, the main difference between the standard approaches that assume that the number of reallocations grow to infinity, right, is that instead of that big O type of thinking, we're really choosing to focus on the problem-specific constants in this case. And the resulting algorithms that we derive, right, as a result, can handle any batch size flexibly. It doesn't really care how many people used your app in the last week. And the great thing about this batching scenario, right, is that then if you assume an infinite batch and derive algorithms, you can deploy all of these policies in a very easy way. Okay. So thanks a lot for your attention. That's all I have. And I'm happy to answer any questions if you have any.
Thank you, Hong. In the chat, I put the link to the interactive website that you mentioned on your algorithm and then the PDF of the archived paper.
Thank you. Appreciate it.
So let's see from the audience. I know we do actually have, I believe, statisticians and mathematicians, along with electrical engineers and machine learning experts on this particular seminar series. So please raise your hand if you have a question for Hong. If I guess I could get us started. So if you go back to when you were defining your optimal cost function or your initial optimization, how did you start to choose? Did you compare a lot of different choices?
Good. Yeah, so we in fact, good. It's an astute observation. So we in fact mainly tried a bunch of different ways of solving that problem and ended up using this particular algorithm that I talked about. So I'm not a control engineer. I don't know this very well. I'm still a student of this discipline. But whenever I talk to WD people, it seems that this idea of an open loop feedback controller, which essentially assumes that anything in the future that you do only just depends on the thing that you know right now, it's a simplification of the problem. That type of a simplification seems to work quite well in practice. And here I think we're simply verifying that time-tested adage. And again, from a formulation aspect, what I really like about this is mostly that I can just try out ideas and see which one works. And we happen to find one algorithm that kind of works well, but I'm sure other people will find better algorithms than this particular one.
And can you also explain a little bit more on the ability to minimize the batch numbers again, because that seemed pretty powerful in terms of your methodology compared to others. And batches, also I'm thinking about clinical or biomedical applications, and that's particularly important in those scenarios where you have limited sample sizes.
Good, good. Yeah. So here the main idea is that if I just take the sample mean by the CLT, it should follow a normal distribution, right? And what this means is that this normal distribution, it doesn't depend on the batch size at all. So the person who's designing and implementing these algorithms doesn't need to know how many people are going to sign up to the trial, right, in stage 1 versus stage 2 versus stage 3.
As long as the
And I
assumption
think
is
that's
that that small batch size follows somewhat of a Gaussian
right, exactly.
distribution. Okay.
And you're already going to use p-values to test hypotheses, right? So as long as you're comfortable looking at p-values in the first place, I think this is actually a reasonable thing to try.
Thank you. There. Audience questions? Well, I guess what is the follow-on to your sequential experimental algorithms? What is the next step that you're doing?
Good. Good. Yeah. So I did write down a couple of different things. So the rough vision that I have for this line of work is really to come up with, you know how like in optimization, as the modeler, you write down your objectives, what you want to optimize, and then you have some constraints and you try to solve for it. And as methodological researchers, people like me come up with a flexible optimization algorithm that can handle any set of constraints and objectives that you might be handing to me. So I want to build up a interface like that, where I ask the experimenter to encode their preferences. And then my job is to come up with an adaptive experimentation strategy for them. And this loop it usually takes multiple years right now, mainly because it's a theoretician writing a theory paper, and that takes 4 years to write and get published. And some of them, the best ones, tend to come up with good algorithms that sometimes get implemented. That's sort of the status quo right now. And I want to reduce that to minutes.
Great. Ambitious, but great, very helpful goal. Thank you so much for being with us today. I'll just let the audience, there's still people who are on the chat. So if there are anything in the chat or if you want to connect with our speaker, his information is in the chat right now. And also you have a GitHub page as well. You can share. Thank you so much. It was really a pleasure to hear about your work.
Thanks a lot, Amina. And thanks for coming, everyone.
Thank you.
Bye.